Aaron Bob with SKA. Work here in the Greensboro office, structural project manager. Tim Cook, who is our senior structural project manager in our Charlotte office, is going to be working on this presentation with us today, and we're going to talk about special inspections, near and dear to us. We are an approved AIA provider, and this is an approved course. So we do get one learning unit for those of you who are tracking it. If you signed up on the sheets in the back, provide your information, name, license number. We'll make sure that we get it documented and recorded for you, and you'll get credit for the course.
You promised me 2 credits.
Clark gets 2 credits. So, special inspections. We're going to kind of go through here. Going through Chapter 17, trying to give a little bit better understanding of the actual specifics of Chapter 17. Kind of answer these 5 questions in a little bit more detail. What are special inspections? Why do we need them? When do we need them? How do we go through implementing them in our projects? And then who ultimately serves as the special inspector? So as we start here, we'll get into what are special inspections. First thing we'll do is define it. Special inspections here is defined by the North Carolina State Building Code. We don't have to worry about it. They tell us what it is. And it's inspections, materials, workmanship, everything that goes into construction for specific materials, construction practices on different projects, provided your building falls into the limits of the code. There's a couple of different types of inspection. There's continuous inspection, which, as the name says, it's a full-time inspection. If the inspector is out there, he's watching, he's in the area, he's watching all of the work that's going on, placement of materials. It's a holistic approach to the observation for the work. Then we have periodic inspection. Again, it's limited. It's limited in time, it's limited in areas. It's something that ultimately is looked at and put together as part of the schedule of special inspections frequently. And it's fluid. It can be adjusted during the course of the project. You know, if things are going well, maybe the frequency of the inspections tapers off a little bit. We're having trouble, we're struggling through it. That periodic inspection becomes more often. But it's, again, the inspector's in the area of the work, he's watching what's going on, documenting, checking for deficiencies. Special inspections is not observations by the structural engineer, the architect, mechanical, electrical, fire protection. All of that, we still have designer observations, still have the construction administration from the design team. It's not to be confused with that, it's a supplement to all of those other inspections, and to help the process, help the reporting, help the quality control and assurance on those projects. History of special inspections. How did we get here? Why did they come about? So we'll look at a couple of collapses, failures that occurred. Most of you probably have heard about the Hyatt in Kansas City. There was failures of a couple of the elevated walkways that happened out there. It happened about a year after the construction completed. There was a big gathering down on the lobby floor. There was a tea dance that was going on. There was about 1,000 people on the lobby floor. And spectators gathered up on the 2nd floor and the 4th floor elevated walkways. There's the 4th floor, 2nd floor. And as they started to gather, the walkways collapsed onto the people down below. 114 were killed. 216 injured. At that point in time, it was the deadliest collapse in U.S. history as far as a structural failure. As the investigation went on, got to see, looking at what actually happened. We have some details down here that kind of show 2 different conditions. The original design, where the hangers for the suspended walkways, which were ultimately supported by the roof, were in line. They came straight on down. The whole path was continuous in those hangars. What actually happened is during construction, they altered the connection It was a quicker, easier assembly for the contractor, but it offset the hanger rods a couple of inches along the box beam. The box beam was in there to support the slab for the elevated walkways, not designed for the hanger load, that point load that was in there. As it was barely sufficient to handle the load from the slabs, so the slabs stayed up and were intact. And when it started to get people on it, watching down at that T-dance, unfortunately that live load onto the walkways caused a collapse. And you can see some pictures here where the box beams, which were not continuous, they weren't a solid tube, they were two pieces. They split, tore apart, the elevated walkways came down. Connection change during the construction. Unfortunate tragedy. Hartford, Connecticut, Civic Center, roof collapsed. Obviously, major catastrophic failure. You can see there's snow up there. There was a significant snow, brought the roof down. Luckily, it was overnight. There was nobody in the Civic Center. However, 3 to 4 hours prior to that, there was a game going on, and there was 5,000 to 6,000 people in that Civic Center. So you can see the potential for human life loss is huge. Again, one of the issues that we got to is there's some connection issues. Okay, as they were detailing the connections, they changed the details a little bit from the construction documents. They offset the centroids for all the engineers in the room. The centroids of the elements were offset. They induced forces into the major members that were not designed for, and we had collapse. Some of the connections were overstressed by 800%. So we're not talking little changes, we're talking major changes to the forces and stresses in those members. Ultimately, it came down. Now what's interesting about this is they actually had some signs that there were issues during and right after construction. They had major deformations in that roof. Huge sags in the spans at mid-span. Again, you get some pretty big deflections. The Coliseum roof that's out here. There's 12 inches of deflection in the center of those super trusses that are up there. It's a 330-foot span, large. But these guys were on the order of feet, and nothing was done. They were good. Everyone assured the contractors, the engineers assured everyone that it was fine, not a problem. In retrospect, it was the structure yelling, saying something's wrong, we need to address it. And to note, that roof, the snow that's on there, while a lot of load, was less than 50% of what the design load should have been. So again, we're not even close to where we need to be. And by we, I mean that. We weren't there. Last one we're going to look at, L'Ambiance Plaza. It was a 16-story residential construction. This was an interesting project because it was lift slab construction technique. I don't know if everyone knows. Lift slab technique is you erect columns vertically. You can see them sticking up right there. And then you cast your slabs. In this case, there was 16 stories, so it would have been 16 elevated slabs that they put. You cast them all on the ground, one on top of each other. You form it up, and then once they're cured, using hydraulic jacks, you jack the slabs up, the vertical elements, shear walls, columns into place, temporarily secure them to the columns until you can come back in and do the permanent connections. It was a proprietary system at that point in time and was contractor driven, the design. It was a delivery method of putting together this building. So while the contractor had engineering designs as part of it, the structural engineers, the architect of record, didn't have a whole lot of input into this delivery method, didn't get the opportunity to adequately review all of the documents, the process, and they ran into a couple of problems. One, the PT tensions that they used, the drape wasn't correct, they weren't out there checking it enough. They had some overstressed concrete around the columns and shear walls where those connections were taking place. And then the actual connections, the angles that they used for the temporary support and for the lifting device were not adequate. And major deformation, the flanges of those angles were bending, the welds were not enough. The entire 16 stories of what they had at that intermittent time collapsed. 28 workers killed, 22 more injured. Interesting to note that following this collapse, they put a ban on this technique for a while, came back and put into effect regulation that required third-party architects and engineers to review any lift slab construction that took place. Third-party peer reviews to make sure that things were going to work following that.
Who was that built?
It was 87 is when this took place. Okay. So, in response to these failures, the U.S. government decided they were going to put together a committee, a task force, to try and figure out what was going on, see if we could address and mitigate some of these failures from occurring in the future. So the U.S. House of Representatives, chaired by that studied the structural failures. And this is what they were trying to do. They were trying to figure out if there was specific elements, certain transactions that took place in all of these cases that were consistent, that if they could address them, they might limit structural failures in the future. In the report, they came up with 22 factors that contributed to the failures. 6 of them they deemed critical. And these are the 6. Communication and organization. Obviously, this is always a factor, whether it's in the design process or the construction. But making sure that we have proper documentation, proper communication, it makes everything flow so much better. Inspection of the construction by the structural engineer. Right there. And not just the structural engineer, but designers in general. But since they were focusing on structural failures, the structural engineer was the focus there. General quality of design. Again, we always strive as designers, as owners, to have good quality, solid designs that take into consideration as many factors as we possibly can think of. Code helps us do that. Selection of architects and engineers kind of comes back to that quality of design. Quality firms that owners hire, that they trust, have good reputation. Hopefully it just helps to ensure the quality of design. Structural connection, design details. Again, in all 3 cases that we talked about, connections were part of the blame. Sometimes significant parts of the root of those failures. And then timely dissemination of data. Again, construction process and durations are quick. They're quick today, they were quick back then. It doesn't look like they're going to slow down anytime in the future. So making sure that people are out there getting the right information, updated information in a timely fashion, in a timely organized fashion, is critical to the success of construction. A peer review process. The subcommittee also recommended a peer review process for construction, design, looking through all of those documents, and trying to catch problems before they occur, and thus the birth of special inspections. So looking at a timeline, first special inspections implemented into Boca, 1988, shortly after that last collapse that we had, that we showed on here. Special inspections into IBC 2000, and then into North Carolina with first and in 2002 version of the code. Now when they did that, it was discretionary. They had language in there that left the actual special inspections up to state construction office, building officials. Certain projects could have special inspections, not everyone had to. Shortly after 2003, I think, is when state construction office first, in North Carolina anyway, started to implement special inspections on their projects. In 2007, there was an update to the 2006 code that changed that. They switched from discretionary to mandatory. So then if you have certain buildings and if they fall into qualify based on criteria set forth in the code, you meet those criteria, your building, without question, requires special inspection. And it's still that way today. Since that time, it's been a key component. It's a very big part, as a lot of you guys know, to the construction process, and it's a good addition to the code. Again, talked about it a little bit before. Special inspections doesn't take the place of designer inspections. The designers of record, all disciplines, still need to come out. And the State Construction Office guidelines make that very clear. It is a supplement. It's additional levels of inspection. It's additional levels of documentation. And it's there to supplement the designer inspections and help the process, not as a replacement. So why do we need special inspections? And we talked some about it, but we're gonna get to some other examples, not just the catastrophic loss. But special inspections are mandatory again nowadays, so we have to do it. But there are a lot of advantages to designers, owners, contractors, everybody involved in the construction process to having special inspections, not just that the code requires it. This is a video that was taken on one of the projects that we were a special inspector on locally. So we did our designer review as a structural engineer, checked all the reinforcing, checked the connections, checked the studs and this composite slab the day before. Concrete placement was happening the next morning, 7 a.m. And here's what we got. So this is 3,500 square foot composite slab construction, and in that time we estimated conservatively, based on records of the weather, that we had about ½ inch of rain. That's roughly 1,100, 1,200 gallons of water that got added into that slab all the way through. So clearly not okay. I mean, most of you know that. Anybody that's worked with SKA or Bob knows that adding water to slabs like that, to concrete, that's a no-no. So fortunately, we were forced to take some core samples, take a look at what it actually did to the slab, because of course the contractor was complaining about how it wasn't fair, it wasn't really that big of a deal. And we had a petrographic analysis performed on those cores. So you can see depth of concrete core. These dashed white lines, probably hard to see, but here's one of them. Here's another one. Here's another one. That's the infiltration of the water into the concrete. This is about the level of the metal deck that was there. So in some areas, the entire concrete on top of the metal deck was compromised by that rain that was coming in. Again, designer inspections took place Friday. Everything looked good, got approval. Without special inspections, chance that crazy rain slab would not have been addressed. We have another example here. This is up in Davie County. So this project's a little interesting. It was prior to special inspections. Structural engineer of record did the design, did our field work. We went up weekly, sometimes more than weekly, to look at all the construction that was going on during the structural portion of the work. What happened is the steel erector, the company for the steel erector for this job was a father and son. The son's children were going to be attending this school the following year. So they were paying a little bit more attention what they normally would to the construction process. And on several occasions during the process, I got photos anonymously sent to me in the mail of issues with the masonry construction that was going on. So we had a steel erector, special inspector. So we went back, we talked to them, we investigated a little bit more, and ultimately ended up with some thermal scans to try and verify. Brian actually helped with these thermal scans. And you can see lintels supposed to be here over top of our openings, missing some places where it's supposed to have vertical steel. Ended up going back, cutting out the face shells of the masonry on the outside before the brick went up. Installed reinforcing steel, because what they did, the mason had the dowels coming out of the foundation, then they would lay up the walls vertically, and then they had the hooks coming out of the top. So it looked like you had your walls reinforced, grouted, just like was normal. Not so much. So we ended up getting it fixed. Like I said, we had a unique special inspector on that project. Helped out a lot. One final example. As some of you may recognize this, High Point. It is the International Home Furnishing Center over there. Constructed 35 years ago, we got a whole bunch of precast concrete panels for the facade. Okay, precast connections in particular are notoriously bad as far as the construction process. We got a call. This is at the 8th floor, this panel, it's hard to see. There's a bow in that panel, and it's right up over here. It bowed out over 3.5 inches, and somebody noticed it. Called, went up and took a look. This is the connection, or lack thereof, at what we found. We got up there. No weld, not even close. That's about 1.5 inches between the plate and the angle that's supposed to be holding. Kept looking. 50% of the concrete panels on this building had deficient connections. 50%. They spent $1.3 million doing nothing but fixing connections. Not seeing it, not improving it, not sealing joints, not anything, literally just holding the panels that they already had onto the building. They would have not had to spend that money, and they had spent a little extra time, had special inspections been in place at that point. So, again, back to the committee report, human errors, omissions, it happens. Most of their studies didn't show that it was intentional. They were intentionally trying to deceive owners, designers, and take the shortcuts, but tight schedules, tight money, that kind of stuff, people are always looking for an advantage. Contractors are always looking for an advantage, and we all know, we've all likely been there, that sometimes you get those issues, just like on these other projects, and special inspections helps to get rid of that, prevent those issues. That, of course, doesn't even consider all of the tragedy to the city, to the lives lost. Again, we're just talking about potential maintenance issues and that other kind of stuff. It could have been bad, don't get me wrong, but precast panel falling 8 floors is not a good thing. But not to mention all of these other structural collapses that we're hoping to not see. So then some advantages. Quality assurance. And obviously, we're talking about making sure that our buildings are constructed the way that they're intended to be constructed. If the SCR, the structural engineer of record, is the special inspector, you get that increased presence out there. The structural engineer knows the structural system better than anyone. The architect of record knows the architectural systems better than anyone. Having an increased presence of those individuals on site, nothing but help the process. The other thing that happens with that is you can answer the questions. Those things come up. Concealed conditions, changes in materials, whatever they might be during the construction process. You have an issue, a question. Having those guys on site on a daily basis, or more frequently, they're going to be able to get to those, investigate the questions, the issues, and response time to any of those construction issues are going to be way, way faster. Which helps contractors, helps owners, helps budgets, helps all of that. And long-term maintenance and life cycle costs too. There is, it's relatively new, so we're still waiting to see how the life cycle costs are going to play out. But there's intuition tells us that it's going to be an improvement. So with that, I'm going to turn it over to Tim. He's going to kind of go through some of the nuts and bolts when special inspections are required and how we address them.
I see how this works. Aaron gets the exciting stuff. I get the boring stuff.
Go ahead. Well, what we're going to try and define now is when are special inspections required. So we have here 2 separate structures. If you don't know, this is a chicken house. And this is a bank. Now, it's debatable which one has more value. I mean, the bank had to be bailed out, the chicken house didn't. So, before we get into when special inspections are required, we need to think about the occupancy categories that the code lays out. Basically, how safe does a structure need to be? And that drives into how important a structure is. And our code defines 4 building types. And I'll start with the most important, and those are the buildings that you really want to be standing in the event of a catastrophe, like a hurricane, earthquake, those are the buildings that you want to remain standard. There's sort of a famous picture around the structural engineering world when an earthquake occurred, and there's a photograph of an ambulance sitting crushed inside the garage that it was parked in. So fire stations are some of the most important structures that we have. Power stations, hospitals with emergency care. Those are the things that you want to keep in operation in a catastrophe. Those are level 4. The next level are buildings like the one we're in, where a lot of people can congregate in one area, where there's a substantial hazard. Turkey house, agricultural facilities where there's a low hazard to human life. So those are category 1, not so important, and category 4, very important. Most buildings around category 2, retail, office buildings, those are all category 2. So to understand when special inspections are required, these are some of the drivers and triggers that set off the chain. So this is, and I know this is difficult to read, but this comes straight out of the code. This is where the code outlines where special inspections are required. Right away, there are exclusions. Category 2 buildings, office buildings, important but not really important. If you're less than 45 feet tall or 3 stories, you're excluded from certain special inspections. Actually, the bulk of special inspections you're excluded from. However, any building that's category 3 or category 4 is required to have special inspections. Next slide. This is basically the same slide, except this is how the State Construction Office presents it. They break it apart into 2 categories. Whole building, which is in red, and then itemized conditions, which are beyond buildings. Retaining walls, for example. Deep foundations, even if you have a category 2 building that might not, from the term of the building, require special inspections. If it has deep foundations, those deep foundations themselves require continuous inspection. We'll get into that later. This is the beginning of a flow chart. So go ahead and do the next one. So you start out, this is your decision tree relative to whether or not you need special inspections. Are you a whole building? Are you a category 2 greater than 45 feet? Then yes. And you break out over here, and here's basically everything that's required by the code. Now I want to focus on these 2 items here. These are sort of separate conditions. When? Let me ask this. Does anybody in here know where the highest recorded wind speed in this state is? I'll buy your lunch if you know the answer. You're right. Most people fall for the, Cape Hatteras, got to be Cape Hatteras. The answer is Grandfather Mountain. And
buy a lot of lunch now.
So anyway, we did some work at Grandfather Mountain, and we learned that the highest recorded wind speed up there was 195 miles an hour, and that was recorded just before the anemometer blew off the building. So basically, special inspections for wind requirements, this is required to be defined by the structural engineer record. So the structural engineer record would see this trigger, and he would outline on the contract drawings, you need to check this building for special wind requirements that I'll describe. But generally, anything over 120 miles an hour. So that would include the coastline, probably 40 miles inland. It's shown in the code, but it's about 40 miles inland from the coast. and those higher elevation areas. And I think there's still in the code the crest elevations where you could actually get up to 130 miles an hour in the mountainous areas. Now, wind speed's kind of funny. Now, I know that I said there's 195 miles an hour was a gust. That was a highest recorded gust. Now, the code defines wind speed as a 3-second gust. So there's a difference between 3-second gust and what they say that the hurricane guys are measuring out in the sea. But anyway, code defines where 120 miles an hour is. Second category is, well, the structural engineer, when the wind trigger is pulled, he'll define these conditions that require a special look during construction. Generally, obviously anything that would be blown off by the wind, cladding, and also the lateral design components, truss hold downs, shear wall, nailing patterns, those sorts of things. And then there's the seismic trigger. If a building is greater than 35 feet, category 2, greater than 35 feet, or if the SDS, which is the sort of the velocity we look at, it's an earthquake factor. If that number is greater than 0.5, and I'm not sure that if anywhere in the state it's greater than 0.5, so that may not necessarily apply to the state, but there are plenty of structures that are over 35 feet. Then the seismic trigger gets pulled. And generally, for a masonry building or concrete building, we would need to look at the lateral resistance components that would resist that earthquake force. Now, we're used to that, but I think where people get tripped is in there are certain architectural, mechanical, and electrical components that are required to have special inspections when the earthquake trigger is pulled. And those are, for an architect, it's the cladding. How well is the brick secured? Do you have veneer, do you really have veneer anchors holding your brick on? Are your precast panels actually welded, for example? And then for plumbing and mechanical, if you're carrying hazardous waste, like hazardous gas, in your ductwork or piping, those have to be specially inspected, and how they're anchored are subject to special inspection. So you go through, determine that your building is required to have special inspection. You check to see if your seismic or wind triggers are pulled. And then once you get past those, you have the general materials. We're still inside the whole building. We're still looking at a building. So now we'll look at the individual materials and components that are required to be looked at as part of the inspection process. I'm certain you can't read this in the back, but this is just the table in the code, and this covers all the steel inspections that are required. There are really a couple of important things that I believe that the code is driving at with steel. And it is connections and just making sure they're using the proper materials. Now, if we look back at why those structures failed that Aaron showed us, they're all generally connection related. The continuous things this is a continuous column. These are things that have to be looked at continuously. Every one of them that we looked at, documented, a report sent to all the players saying this is okay or it's not okay. And if it's not okay, then it has to be documented when is it going to be okay, so that we can move on with our construction. So this is the continuous column, and what is triggered in this continuous column is driven around the connections. For example, this bullet right here is slip critical joints. That's where when you're bolting something together, you have to bolt it tight enough so that the plies don't slip. These down here are special big welds, I'll call them, like full penetration wells, wells that require more than one pass. Now, as a structural engineer, what we try to do is we try to avoid those things. We try to avoid the complicated wells. We try to make our connection simple. For example, I don't know that I have ever used a slip critical connection. I always use a snug tight bolt type connection, where you bolt it together, you pull the plies together, you can see the bolts in there. The bolt doesn't depend on the slip. It just shearing the bolt. I try to design around a 5/16 inch fillet. That is the maximum fillet size you can use that can be visually inspected. It's a single pass weld. Those don't, anything bigger than 5/16 require special inspection. 5/16 and less can just be a visual evaluation, a periodic visual evaluation. So you try to drive your design around, not trying to eliminate special inspections, but special inspections can cost the project money. And so if you can drive your design around trying to limit things like this, you can save some money in the project. This is just a continuation of the steel part. This part here, we're continuing in the welding component of the materials. This is welding of rebar. Again, there's a lot of Southern Carolina people in here. Have we ever welded rebar? I mean, is that a common thing that we do? No, because it's hard. You have to have a special kind of material to do it. You have to have a special guy out there to do it. It's something you just try to avoid. So, and when you do it, here now you got to go and pay an inspector to come look at it. This is the concrete, so we've got steel, now we've got concrete. And when you think about concrete, what are the things that you, I guess, question the most about concrete would be, well, it's a mixed product. How much control do you have over the mix? So that's one of the things that's really a trigger in the continuous part of measurement of the wet property, plastic properties of the concrete. Every time you take a strength test, every time you take cylinders, the code tells you, okay, we also want you to measure slump, temperature, all those other things that might be a trigger to tell you something's wrong here. And then another thing that requires continuous inspection is the actual placement of the concrete. So you can see why inspection during placement is important. We saw the video of the rain. Concrete is at its most vulnerable place as it's being placed. And lots of bad things can happen. Now we'll get into a little bit of masonry. This is just straight out of the code, and really what I'm just trying to show you here is these are exceptions to the requirements for masonry inspection. Generally, they are the empirically, there are certain things in the code that have empirical designs. However, most everything we do is an engineered design. Everything that is an engineered masonry design, empirical meaning that the code tells you specifically how many bars to put in this kind of wall or this height. Those things do not require special inspections. However, the code sort of limits where you can actually use empirical design. So most everything we do is an engineered masonry design, and that is an immediate trigger for a Category 2 or Category 3 building. And here are all the requirements for masonry. And here you see that the continuous things are primarily, again, welding of rebar, and installation of the grout. There's the grout properties. And this is measured in pre-stressing force if you ever do pre-stress masonry. But being there as the grout is being placed is a requirement of a continuous inspection. And that goes back to Aaron's school. if someone had been there continuously, they would have seen that these cells that are allegedly filled are not being filled. The other special thing about masonry is grouting masonry can be tricky. If you don't have really excess water in your grout, the block will suck the water out of the grout and the grout will hang and won't make it all the way to the bottom. So special inspection of the placement of grout and masonry is important. This is just a continuation of the masonry table. I'm not going to bore you with it. So. This is the wood portion. Wood doesn't get a lot of attention relative to special inspection. The primary thing with wood is that the prefabricator, for example, the manufacturer of the prefabricated trusses, the manufacturer of the TJIs that are glued together, those sorts of things require a qualification of the manufacturer who's providing them. That qualification also exists for steel fabricator, and generally those qualification processes for precast concrete folks, wood, and steel is that they have a certain quality control and can show that they can control the quality of their product and can take you back to the exact material, to the exact mill where the material came from. That's a little sidebar about qualification of fabricators. But back to wood. Wood is, the thing about wood is that they're driving out here is lateral load resistance. Shear walls, I don't know how much familiarity you have with plywood shear walls, but they can be very difficult to construct. For example, if you overdrive the nails in the sheathing of a plywood shear wall, you lose 25% of the capacity. You get your nails too close, the capacity of the shear wall to the edge where the joints butt together, the capacity of the shear wall is gone. So in a high load situation where you're using and counting on plywood shear walls, it's important to have a shear wall inspection. Now, with that in mind, I want to speak for a moment about the engineer of records involvement here. We talked some about continuous inspection, we talked some about periodic inspection. In my mind, it is the engineer of records' responsibility to do a good job and give the statement of special inspections a fair shake and clearly define what he thinks is important to be inspected. He knows where his weak links are. He knows where the soft spots are. So to me, it's up to him to determine and show the contractor and the special inspector who is a different person what's important. These tables that I'm showing you, these are the minimum, the code minimum. The engineer of record certainly has the right and the responsibility in some cases to go beyond where he thinks he might have trouble. So those are the whole building parts: steel, concrete, masonry, wood. Now we're going to look at these itemized pieces real briefly. And they start with the soils. And you'll notice here, this top table is related to spread footings. Spread footings don't get a lot of attention. The only thing you need to worry about as far as a spread footing is a periodic check of the allowable bearing pressure. But if you're placing spread footings in a field type situation, then that field has to be continuously monitored. Beyond that, we got these two tables here are deep foundations. Any type of deep foundation requires a continuous special inspection. That'd be helical piers, pin piles, caissons, driven steel piles, whatever. If it is a deep foundation, it requires a continuous monitoring. And this is the code reference to those type deep foundations. skip ahead a minute. Last three things. This covers spray on fireproofing for any structure. If you have spray on fireproofing, that needs to be inspected. Even if your structure is a type 2 structure and it's only 1 story tall, if it has spray on fireproofing, that is required to be inspected by the code. Now, what about a type 1 structure? Well, how many type 1 structures have spray on fireproofing? Not many. So I think just by exclusion there, the type 1 is out. So let's go back to it. Similar to spray on fireproofing, this is intumescent fire coatings. Those have to be checked by the code. Again, we're talking about, you have to think sort of in terms of catastrophic events and what would happen if the fireproofing wasn't there. That's just as important as the structure itself. When fire breaks out, you obviously want your structure to stand. There's a section on eaves, but the eaves, if your eaves is a drainable system and it's applied over a water-resistant membrane, it doesn't require special inspection. If it's applied over masonry, it doesn't require special inspection. So I guess some of you other SKA people probably know eaves better than me. There are some systems that are just pure barrier type. Those have to be specially inspected. And the last section are special cases. A special case is anything that we haven't covered before that this engineer of record feels like ought to be there. So he has a responsibility to define things that require special inspection. For example, carbon fiber reinforcement and the fire protection that would be applied to the carbon fiber reinforcement. So again, it's up to the engineer of record to, this goes back to the statement of special inspections. This engineer, and I think really, I guess in my experience, I think the statement of special inspections kind of gets glossed over a little too much. And I think the engineer of record needs to take responsibility and clearly define what is going to be specially inspected on any particular project. I can see special cases here being left out because it's not defined in the code, but really there are things out there that require special inspections that beyond what the code would say. So turn it back to Aaron and tell you how to save money.
So, with all that, we'll get into what a lot of people want to talk about with it, fees and potential savings. So obviously increased inspections increases cost. I mean, it just is what it is, whether it's the engineer of record, whether it's a third-party structural engineer, whether it's a construction materials testing, and we'll talk about some of that in a little bit. There's fees that are associated with those services. State Construction Office has got some data that they've recorded over the last few years, and they're tracking special inspection costs running between 0.25% and 1% on the projects. Now, obviously, Tim just went through a bunch of different potential types of projects. Obviously, materials, masonry versus steel, how big the project is, what types of finishes are in the project can ultimately affect the percentage that you have there. As owners, as architects, as engineers, we want to make sure that people are budgeting money for special inspections. All the resources that I found say that a 1% budget for the construction cost is a good starting point. But in reality, once you get to the statement of special inspections, once it's been developed, you have the construction documents and you're starting to put that into plan together, you get schedule of the contractor affects the construction cost, the special inspection cost. At that point, you revisit it, you go in and you look and you see what the actual cost is. Get a cost from the special inspector. But we do have some potential for savings. We talked about the precast panels and the $1.3 million that was spent for literally fixing connections. We had a project that our Building Solutions group worked on a little while ago where they put a whole bunch of masonry retrofit anchors into a facade to stabilize that facade. It was part of a $2 million project, and it was a lot of costs that went into it. The entity has since had us perform special inspections, visually observing masonry ties, even though it's not technically part of the masonry code requirement for special inspections. We've gone through, we've done increased inspections to ensure that masonry ties are installed as they're supposed to, because $5,000, $10,000 of time during that inspection process probably saved $500,000 worth of masonry retrofit actions. So there are advantages, there are potential cost savings down the road to having those elevated inspections. Lastly, we're going to talk about who is the special inspector. Who can be, who does the code require, what do you have to do, all those types of questions. So, part of the code, as for application with a permit, you have to employ a special inspector. Again, our building falls into that special inspection realm, whether it's a whole building, whether it has segments of it that have to, you have to have a special inspector. You have to engage that person. So, they have to be qualified. There's a lot of text here, but essentially what it is you need a qualified agency to be the special inspector. Your SI must be a registered, licensed engineer or architect. Typically, it's engineers rather than the architect, but an architect, a licensed architect, could serve as a special inspector. We're talking about 5 different potential arrangements for how to employ a SI. First one is the structural engineer of record serves as a special inspector. Just the SER. It doesn't happen a lot because most structural firms don't have geotech. They don't have materials testing as part of it. And some of that stuff with the spray fireproofing, the intumescent, you need to be able to measure that and have testing, bond test, thickness test. A lot of structural firms are not set up for that. A lot of structural firms don't have soil. They don't have geotech in-house. So again, you're talking about potentially needing to have additional people, additional engineers come in to help with that process, which is the next one. The structural engineer serves with other subs. This is what is used when we do it, as SKA does the special inspections process. We typically work, and I actually am a fan of this process because it gets, if you're working with the company who did the geotech, you have the geotechnical engineer of record that's working with you. So not just one engineer of record that is serving as the SI role, but you have 2. So part of the design team, increased communication, you have that expert that's on your team. And normally those geotech companies have materials testing as well. So you're keeping the 2 entities working together, better communication, better flow of documentation as you go through. And it's worked pretty well for us. It keeps the structural engineer engaged who is most familiar with the structural design. You know, they're part of that design team. They're out there looking. Tim was talking about being aware of the most critical components. The structural engineer of record he knows where the high stress areas are, so he's gonna make sure that those parts of the building are really watched carefully. Another option is third-party structural engineer serves as the SI for full scope. Again, same limitations as the first one. It's a third-party structural engineer. If the SER who is on the project doesn't want to do special inspections, doesn't have that capability, looking at a third-party structural engineer is a good option. They still are familiar with the material types. They're still familiar with load path. They're still familiar with structural design, and spending some upfront time for them. They'll get up to speed on the actual building, talking with the structural engineer record. They're good for looking at what areas are critical. Third-party SE with sub-consultant, same kind of thing. Again, just third-party engineer, all the same pros and cons that go along with it. The last one that is used a bunch and is a third-party, non-structural engineer of materials testing. Again, they have engineers on staff, typically not structural engineers, but licensed PEs. The good thing with this is that they typically tend to be SI as well as material testing. So it's one entity that is providing all of the documentation. Non-SE, but they do have the testing agency that's there. Again, the communication is good at that point. You can go about hiring SIs a couple of different ways as part of the designer of record contract. Most of our experience hasn't been that way, but you can do it as a supplement to the designer. Usually it's through a separate contract. Again, you go through, you figure out what firm it is, whether it's through an RFQ process or just quick solicitation of a couple different firms, and you have a separate contract with those individuals. What goes into getting your costs, getting qualifications, all that kind of stuff. And lastly, we're going to go through some of the actual qualifications. Again, we talked about your SI's got to be a licensed engineer or architect in the state of North Carolina. Your primary inspector, your secondary inspectors, they also need to have certifications. It doesn't have to be a PE. You can EIs, engineers in training can help, can go out and do the inspections. You can have certifications from your different professional organizations. ACI has multiple levels of certification for different types of concrete inspection. Steel, welding, AWS, CWI, all of those organizations that have different DOTs, they have different levels of certification. Again, the point is, you've got to make sure that somebody who's out there looking at it is qualified, they know what they're looking at, and they have certification to a licensure saying that they're that. Because, again, having just anybody out looking at it, writing stuff down is not really the intent of the special inspections process.